All right. So, well, I guess I shouldn't have started yet, but I did. If you haven't picked up your test, you can pick up your test. I don't want them. One thing I wanted to highlight is that I contacted the other instructors because I think we're scheduled across 3 rooms. But I asked them if they wanted to stay across 3 rooms. It always gets super confusing, especially for students. And so we will be in here, which is our room. So our final exam will be in here. And then I've kind of sorted out everyone else. They can have their own rooms. And so even though there are 3 rooms listed, we'll be in here. So that's pretty rare, actually, that you get to have a final exam in the room that you had your class in. But then you can rely on all your memory triggers. Oh, the periodic table of elements tells me everything I need to know. No, it doesn't. Maybe you could get there, use it to your advantage. There's 2 of them in here. I think there's only 2. Yeah. Okay. So we've landed on just the one room, even though it's kind of confusing the way they've got it listed. Okay. All right. So has my formula sheet loaded yet? No, it has not. This is section 6.2. So last day we finished one sample proportion type questions. And so today we introduce our second type of question, and I'm just going to call it a 2 sample proportion type of question. 2 sample proportions. Now I guess I could, whoa, are you ready? It's on the back page of our formula sheet. We're chipping away at this thing. Pretty cool. Or I think it's cool. I don't know about you. It is cool. Okay. So what I want to do, and I was going to copy in the formula sheet, but I guess not. I need lines. Let me just disconnect here and add. I don't know why it won't let me do it. Probably can, but I don't have the skills to do it while it's hooked up. So let's, uh-oh. Now I've done it. Okay. So a difference of 2 proportions. So as opposed to 1 sample proportions versus 1 sample proportions, which was our first type of question, was 1 sample proportions, or 1 sample proportion singular. If I have 1 sample proportion, what did I want to do? I wanted to compare it to some value. I was hypothesizing how this thing would compare to a value, right? And so for 1 sample proportion, we compare our sample proportion to a hypothesized value, a hypothesized proportion, which we called P naught. Well, that should be a 0. The hard part was figuring out what value you wanted to compare your sample proportion to. And so in a way, I find that when we move into 2 sample proportions, it's a little bit easier because now what we have is I've collected 2 different samples and I want to compare those proportions to each other, right? And so here, now, we want to compare the sample proportions to each other. Kind of as a guiding example, right? If I say, well, we've got some election data, right? We can talk about the proportion who voted. Let's do NDP just because I guess they won. It all feels like it's kind of inconclusive still, but I think it's been declared. Who knows? But the proportion, and I should have pulled the real data, who voted NDP in where? Well, I live in Kelowna Center, which was up in the air for a while. It was some percentage. Probably, now I wish I had it. Does anyone have the election data handy? And then what else do I want to do? Maybe, I don't know, what's a fun one? Vernon. I don't know. And in Vernon, oops, I should capitalize Vernon, how rude of me. Blank voted NDP. Let's see. Is my internet good enough? Elections BC, sure. Looks like I've been there before. Okay. Dun, 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 dun. I should have picked some that were closer to the top. Okay. How about I change it from Vernon to Kamloops North Thompson because they're on the same screenshot. I know, cheeky. Cheeky, cheeky, cheeky. Come on. Driving me bonkers. There. I'll change this to Kamloops. Oops. Skip the A, I guess. So you could formulate this as a question. Kelowna Center, NDP, 42.7%, or we also could have said 10,993 out of 25,747 voted NDP, right? Or we can talk about the proportion. So 0.427 or 42.7% of how many votes? 25,747 votes. And in Kamloops, I changed it to Kamloops to be on the same screenshot. That was rude. And in Kamloops, 0.329 of 30,009 votes we're for the NDP. Oops. Trying to write too quick. And doesn't like that. So now, right, I have a sample from Kelowna Centre and I have a sample from Kamloops. The sample are those who went and voted. And so maybe not necessarily representative, but let's assume that it is. So now, what do we want to know? Is there a significant difference in these proportions? And so here, what we're going to be asking, if I have two samples that I want to compare to each other, right, is there a significant difference in the proportions? If we let, just generically, P1 hat be the sample proportion from sample 1, sample proportion from sample 1, then of course P2 hat is the sample proportion from sample 2. I also have sample sizes. N1 is the sample size of 1. That doesn't make sense. Of sample 1 and N subscript 2. So we use subscripts to denote which group they're in. Is the sample size of sample 2. So here we use subscripts to denote which group or which sample information is from. We could also talk about X1 and X2. In this case, we didn't have X1 and X2, but instead of P1 hat and P2 hat, what could we have said? We could have said 9,874 out of 30,009 votes from Kamloops North Thompson was in favor of the NDP. And then you could calculate your proportion, right? And so we also could have X1 is the number of successes from sample 1. And of course, X2 is the number of successes from sample 2. Depending on what information you have. What's really nice is there's still a limited amount of information that you need in order to answer these questions. Let's see if my formula sheet has loaded yet. It's still loading. Okay. That's okay. I still have more to say. So, besides the formula sheet. In fact, let me add a page. What if you didn't want to talk about the NDP? You've got the Green Party in both cases, right? The Green Party, you've got the Conservative Party in both cases. You don't have, I guess, an independent, but he's not labeled an independent. I don't know. So you can't compare those two samples, but you could pick a different success, right? And talk about those proportions, right? If you wanted to talk about the Green Party or the Conservative Party, you have information from both samples. And so you could easily redefine your success and compare those proportions, right? And so if I want to know if there's a significant difference in the proportions, right? Now, are they basically the same enough? Is kind of what we want to know, right? And so we know that 42.7 or 0.427 and 0.329, they're different from each other, right? But we want to know, are they far enough away from each other to be considered significantly different? Okay. And so for that, we need to take into account the spread of this distribution. Now, for us, we're not going to spend a ton of time talking about, okay, what is the sampling distribution of the difference of proportions, because we're just going to use the formulas from here on out. But it helps to know that there is a sampling distribution. But what we want to do is we want to compare P1 and P2, right? Ultimately, we want to use these sample proportions to learn about the overall population proportions. So the easiest way to do that is by subtracting the two, right? And so we can do P1 minus P2. Then what we can say is, okay, if P1 minus P2 is 0, then there's no difference between these two. They're basically the same, right? Not significantly different. And so then there are, I should clarify, P1 and P2 are not significantly different. Whereas if P1 minus P2 is not equal to 0, right, or not essentially 0, then there is a difference between these two. And we can talk about it being less than 0 or greater than 0, right? But then P1 and P2 are significantly different. So when we build our confidence interval and when we do our hypothesis testing for two sample proportions, we're really hypothesizing about the difference between P1 and P2. So when we build confidence intervals and do hypothesis testing for two sample proportions, we hypothesize about P1 minus P2. How does P1 minus P2 compare to 0? There is a kind of an optional section that we're not doing, but you can do not equal to 0, but all the rules that we're going to establish have to do with around centering the difference at 0, which is fine. That's like pretty standard. So now what you're going to have if you don't know P1 and minus P2, your point estimate for P1 minus P2 is probably going to be P1 hat minus P2 hat, right? Your best guess at what this thing looks like. And so your point estimate is going to be P1 hat minus P2 hat, right? Your best guess at what this thing is. Now, I want to talk about the conditions, but I'm also kind of impatient. Okay, I have my formula sheet, so that's good. It has loaded. I don't know why it keeps reloading, but that's okay. Let's get the conditions out of the way. We know the conditions for one sample proportion, and now they're just going to be the same, but for each sample, right? And so the conditions stay the same. The conditions the same as one sample proportion but for each sample which means our independence condition, and I'm going to add one, the independence condition, which was I have to have a random sample, is now going to morph into each sample has to be random, or we have to assume that it's random. Each sample is randomly selected. What would you do for the election data? Votes aren't randomly selected. So then what are we going to do? We're going to say, okay, they weren't randomly selected. We own that. But I assume that my sample of votes, or these votes, are representative of the population. Right? So in this case, or assume the samples, potentially two, are representative of the population, of the populations, I guess. That's just an assumption. So as long as you state your assumptions, you're allowed to assume those things. The n less than 10% condition now applies to both. N1 has to be less than 10% of its population, and N2 has to be less than 10% of its population, just not taking too much of the sample. In the case of votes, we just take it as it is, and so that's fine. But now this new one that we add is that the samples have to be independent of each other. The samples are independent of each other. For the normality condition, for the sample size condition, I'm going to underline here. Again, we have different conditions, different normality conditions, depending on if we're going to do a confidence interval or a hypothesis test. And so for a confidence interval, I'll just say in words, we have to have at least 10 observed successes and at least 10 observed failures in each sample. Need at least 10 observed successes and at least 10 observed failures in each sample. Effectively, you want n1 times p1 hat. Uh-oh, it went dark. Is my Zoom still with me? Okay, that's good. Kind of confusing though. Why did my screen go dark? I'll never know. Which is x1 has to be greater than or equal to 10. But then the second sample also has to work, which is x2 has to be greater than or equal to 10. I need the same number of failures, which I can do n1 times q1 hat, n1 times q1 hat. At this point, we should be pretty comfortable with the q's because they're just the opposite of the p. So of course, q1 hat is just 1 minus p1 hat, or n1 minus x1 if you prefer. Right, if they're not a success, they have to be a failure. And I need n2 times q2 hat, which is n2 minus x2, also has to be greater than or equal to 10. That's if you're doing a confidence interval. If you're doing a hypothesis test, remember that's when we used our p-naught to check our conditions. But now I need at least 10 expected successes and at least 10 expected failures each sample. Okay. Now the expectation gets a little bit tricky. Okay. What we're gonna do is, and I'm just going to kind of run through it because this is not theory that I expect you to have a handle on, but if you're interested, we're assuming that these two sample proportions are the same until we have proof otherwise. If they're the same, I should be able to push them all into a pool and they can all just kind of swim and be all the same. And so what we do is we use what's called the pooled proportion. Instead, or to find the expected successes and failures. Now, the pooled proportion is exactly as it sounds. P hat, context, if you're dealing with a two sample proportion type of scenario, P hat now is going to be the pooled proportion. pooled proportion. Sometimes we'll put a little pooled on there. I usually don't though, because the context will make it obvious. But the pooled proportion is going to be the total successes over the total sample size. So you just push everyone in the pool. And if you're a success, you're a success. It doesn't matter. And your total sample size is now both sample sizes combined. I do want to make a note here. I usually write p hat, not p hat pooled. So I need you to be aware of that. And that the context will tell you that this is no longer a one sample proportion, it's a pooled proportion for two samples. Okay, so how are we going to check this? Once you have your p hat, your pooled proportion, then you can take n1 times p hat has to be greater than or equal to 10. N1 times q hat has to be greater than or equal to 10. N2 times p hat has to be greater than or equal to 10. And N2 times q hat has to be greater than or equal to 10. That's a lot of math for no marks at all. In fact, you won't have to do the math. You'll have to check whether you want the expected successes and failures or the observed successes and failures. And so that's as far as I'm going to take it on a test, but you'll need to know it just in general for assignments and things, but not on the test. Okay. I think we're ready. Hey, it was loaded and now it's not loaded. Dang it. Am I gonna have to do the same thing I did before? General course material, maybe. Bring into here. It's gonna be like my billionth. Oh, okay. Time I bring in the formula sheet. All right. If you don't have a copy of the formula sheet, it might be nice to have one. I brought some here. Because check this out. All on the second page here. It's huge, but let's just chip away at this thing. There's lots of clues on here too. So from your formula sheet, two sample proportions. So once you've identified that that's the type of question that you have, then you're only working in this section of your formula sheet, right? And you know that this first bit, that's just theoretical and you can ignore it, right? This is just theory. We can ignore this. It's what we're building off of. So it would be kind of weird of me to not include it. But kind of the greatest finding is that the difference in proportions still follows a normal distribution, which is awesome because we know how the normal distribution works. It's going to be centered at P1 minus P2, and it has a standard error of it's big because now I have information from both samples that I need to take into account, or both populations. So if I want to build a confidence interval for the difference in the proportions, we said, okay, my best guess at what that difference is P1 hat minus P2 hat. It doesn't matter which group you assign to be group 1 and group 2, as long as you're consistent. You don't want to be switching group 1 and group 2 halfway through. But if you say, okay, Kelowna Center is going to be my group 1, and Kamloops North Thompson or whatever it's called is going to be my group 2, as long as you're consistent, it doesn't matter. Hey, something we know how to find, Z star. That's the exact same Z star that we were using before, right? So if I say, okay, I want to make a 95% confidence interval, then you know how to find that Z star, right? You use the table 95 and you get a Z star of 1.96. So that's nice. You already know how that works. And then we've got this big square root, which is very similar to what we had before, right? Where we had the square root of P hat Q hat over N, but now I have P hats, Q hats, and N's from both samples. And so it's just been modified slightly to accommodate both samples. But it's on your formula sheet. So besides it being the math being a little bit bigger, there's nothing crazy going on here. Okay. Hypothesis test. We're hypothesizing about how P1 minus P2 behaves. Yeah. One of the things that I tend to do is I tend to write it like this. But why is that the same as P1 minus P2 is equal to 0? Well, if P1 is equal to P2, then you have P2 minus P2 is equal to 0. Fine, that's the same. And so here, I'll say this. These are the same. I'm going to try to use P1 minus P2 is equal to 0, just because it has that P1 minus P2 in it. Okay. Versus the null hypothesis that P1 is equal to P2. I'm fine with you using either one, right? But then if you are hypothesizing that P1 is equal to P2, that makes it easier in the beginning, I think, because then you can just say, okay, the proportion in Kelowna Center is the same as the proportion in Kamloops North Thompson until I have proof otherwise, right? And so for me, this one is kind of more intuitive to wrap my head around, but because we're going to be working with P1 hat minus P2 hat as my point estimate, that's the reason that I would use this compared to 0, right? So it doesn't really matter. Now, this looks big, but it's really only because I have written it 2 different ways, right? So this is the same thing written 2 ways. Written 2 ways. Pick one that you like and ignore the other one. I do want to expand on this though. Z is a standardized value. So anytime we're standardizing, we're going to take our point estimate minus the hypothesized value. Oops. Divided by the standard error of the point estimate. Now, the standard error of the point estimate happens to be kind of gross. But why do we only have P1 hat minus P2 hat here? That's my point estimate for P1 minus P2. But then my hypothesized value for the difference is 0. I hypothesize that P1 minus P2 is 0. So from here, I'm really just seeing how far is my point estimate from 0. Right? So we don't even write that typically here. Right? Really what we have is how far is this from 0. But to make it a little bit cleaner, we drop that. Right? Same thing here. How far is that from 0? Now there's clues here. So P hat, Q hat has just been distributed over the fractions. I tend to use this one, this version, this first version, because then I can simplify these and I can kind of simplify this into one number. And then I only need to work with P hat, Q hat once as opposed to twice. Doesn't really matter. But where P hat is the pooled proportion estimate, which is that one that we were talking about. So even though this looks huge, this is just a little cheater note, right? P hat is the pooled proportion, which is the combined number of successes over the combined number of cases. Depending on the information that you have, if you have the raw successes, you can just use that. If you don't, then you have to do a little bit of work to find the successes, right? By taking n times p hat for both. But usually you just have this, and then you can find p hat that way. Okay. I'm going to skip the conditions, but let's answer that question that we set out to answer in the beginning. Whoa, a long time ago. I'm going to copy this. Okay. I'll remove the highlights. And is there a significant difference in, how can I say this, NDP votes, or whatever group you want to talk about, in Kamloops, North Thompson, and Kelowna Center? Let's grab some information that we need to answer this question. Now that you know how to do this for two groups, right? You could compare any two groups that you're curious about. So that might be kind of fun. So if we're talking NDP, then we have to compare apples to apples, of course. And so I need I have my successes, I have my proportion, and I have my n. So I'm feeling kind of rich with information here. And so let's summarize this beside here. So I have x1 is 9,874. I guess I should first let Kamloops be group 1. Usually I just do them in the order that they appear. Right. So here X1 is 9,874. N1 is 30,009. Now, if you did 9,874 over 30,009, you should, if they've done their math, hopefully they use software. I'm not entirely convinced that they did. So let's do, for p hat, that's going to be X1 over N1 divided by 30,009. Phew. So P1 hat is 0.32903462229, blah, blah, blah. But let's just use what was given. .329. Right. We understand that some rounding happened. That's okay. If I let Kelowna Center be group 2, X1 is 10,993. And, oops, sorry, group 2. Nice try, Emily. X2, N2 is 25,747. And P2 hat is 0.427. I only need 4 of these 6 pieces, right? But in this case, we're rich because we have all the pieces. So that's cool. Now, what I would recommend before you even start your hypothesis testing, because when I ask you, is there a significant difference? Then that's your clue that you have to do a full-on hypothesis test. Now, what's really nice is we're going to follow those same steps that we established, right? Using the new formula for Z and the new null hypothesis that we have. But besides that, everything works the way we expect it to. The first thing I would do is calculate the pooled proportion, okay? Just so that we can get it out of the way, and then we'll have it. So I calculate the pooled proportion before starting my hypothesis test. Now, kind of overwhelming from your formula sheet, right? We have the pooled proportion down here. That's a lot of information. But it's because we might have different information in different scenarios. And so the pooled proportion is, I have X1 and X2 and N1 and N2. So why not just use that? Right? I have X1 plus X2 over N1 plus N2. So my pooled proportion is going to be 9874 plus 10993 over, I want to say 30,009. But let me confirm. Yeah. And 25,747. I can combine these, right? If they're all basically the same, 9874 plus 10,993, I get 20,867. But I always tend to muck it up when I'm doing it on the fly. So if you get something different, stop me. 30,009 plus 25,747. 755, 756. I'll do my pooled proportion to 3 decimal places to match what was given. And so I have 20,867 divided by the previous answer, 0.3742556855. To 3 decimal places, I get 0.374. One thing to check is that your pooled proportion is just a mashup of your other 2 proportions, your 2 sample proportions. And so it should be in the middle, right? Should be hanging out. So 0.374 is somewhere between 0.329 and 0.427, right? So that's one way that you can check your pooled proportion, is to make sure that it's in the middle between those 2, because it's just a mashup of the 2 individual proportions. And so here, check the pooled proportion is between P1 hat and P2 hat, which it is. Okay. So my pooled proportion, if the 2 groups are the same, I should be able to generalize with 0.374. If not, then that's not the case. Okay. We wanted to know if there was a significant difference between these 2 groups. I guess I can't really use I'll abbreviate this to KC, and this can be KNT. I would have preferred to use just singular subscripts, but I want to have question-specific subscripts, especially in my hypothesis, because if you haven't defined what group 1 and group 2 are, then it's really hard to know, okay, how do I think these 2 compare? I just want to know if there's a difference in these votes. And so for my first step in the hypothesis testing, now I'm ignoring the conditions because the hypothesis testing is way harder. So we're just going to jump to it. First thing we need to do is state the hypotheses. Now, from your formula sheet, you have 2 options. All right, I'll go grab it from our formula sheet so you can link the 2. Now, what I want to see here is we need to use question-specific subscripts at least in the hypothesis. I don't really care about in your calculations. At that point, you've established which group 1 is and which group 2 is. But for the test, I want to see question-specific subscripts for the hypothesis, for the null and alternative hypothesis. So what I mean by that is my null hypothesis could be the proportion. Now the population proportion which would include everyone in Kamloops North Thompson that didn't vote. P and then the subscript K and T, because otherwise I'd have K and K and it didn't really work. I should have used the one below in the table, I guess. Wasn't thinking. Is equal to the proportion in Kelowna Center. So what I mean here is like that. If I want to know if there's a difference between these two, my alternative hypothesis still has to be about these proportions and how they relate to each other. But if I want to know if there's a difference, then I'm going to have a not equal to here, right? Kelowna or Kamloops North Thompson is not equal to the proportion in Kelowna Center. Or if you prefer, kind of separating these two, because you've got NOR here. So it looks overwhelming, but that's just because I want to try to give you as much as you could possibly want. Or you could say the null hypothesis is that, and I still want to see those question-specific subscripts, PKNT minus PKC is equal to 0. Or in that case, the alternative still has to be about how this difference relates to 0, but now I want to know if it's not equal to 0. So PKNT minus PKC is not equal to 0. You only have to do one of those. I'm fine with whichever one you choose. Okay. Old habits die hard for me, so I might stick with this one, but I'm trying to move towards this one just to emphasize that, okay, I'm really comparing the difference in proportions to 0. Okay. Gets tricky though. If you want to show that the proportion in Kelowna North Thompson is significantly, which was it? It was less. If we want to know if it's significantly less than Kelowna Center, what would that do to our 0? Then if this is smaller than this would become negative, right? Think about 1 minus 2 makes a negative, right? And so then it would be less than 0, which is not as obvious to me as just using a less than here, right? So just kind of getting comfortable with those two options and picking your favorite, and then you just have to do one. In either case though, if I have not equal to, I have a two-sided test, which means that way later in step 3, I need a two-sided p-value, right? And so this is a two-sided test. And I kind of just parking lot that until step 3, where I need to figure out, do I have a one-sided or a two-sided p-value? Step 2 is, I call it do the test, but I'll be proper, calculate the test statistic or do the test. Do the do. From your formula sheet, you know that after your null hypothesis, you're given your, hey, Come on. It is not letting me make this bigger, so I guess we're stuck with that. Like a fool, I'll try again. Why isn't it letting me do it? Oh well, I'll just zoom in, I guess. Now, I'm going to ignore this one, right? Pick one that you like, pick one that makes sense to you, and ignore the other one. And so for me, Z is going to be P1 hat minus P2 hat and for now, I'll show that technically it's how far is that point estimate from 0, right? Or, I mean, even more theoretical, how far is that from P1 minus P2? But assuming that the null hypothesis is true, which says that that's 0. Assuming H naught P1 minus P2 is equal to 0 is true, makes this equal to 0. Because we do all our testing assuming the null hypothesis is true until I have proof against it, right? Until I found that, okay, that's actually pretty unlikely, then I can reject the null hypothesis. So technically that's all going on there, but effectively we just have P1 hat minus P2 hat in the numerator. Then I have P hat Q hat times 1 over N1 plus 1 over N2. This P hat is the pooled proportion from earlier. Now, if you didn't have it and you hadn't checked the conditions, because then you would need it to check for the expected successes and failures. But if you didn't have it yet, you would need to calculate it here, kind of somewhere. We know from earlier that it was 0.374, I want to say, 0.374. So then I know also that Q hat is 1 minus 0.374, which is what? 0.626. Oops. This version of the formula that I crossed out, all it's done is it's taken this P hat, Q hat, and multiplied it inside, right? And so then you get P hat, Q hat over N1 plus P hat, Q hat over N2. But I just like to extract it on the outside. Okay. I have P1 hat, I have P2 hat, I have P hat, I have Q hat. Whoa, so many P's. You thought you'd run out of P's. P values. Nope. Lots more P's. And then I have N1 and I have N2. So I'd say we're ready to rock and roll here. Z is P1 hat which was 0.329, and P2 hat is 0.427. One thing that I'm being sloppy about here, that I'm okay with you being sloppy about as well, is I just use the 1s and 2s. And so the question specific subscripts, I really only need to see them in the hypothesis, because that's where you're establishing how you're going to compare these two things. And then if you just use 1s and 2s in your Z, that's fine. because it gets super boggy trying to replace these with your question specific subscripts, and you don't really need to. Divided by the square root of 0.374 times 0.626 times 1 over N1, which I want to say was 30,009, plus 1 over N2, I'm going to guess 25,747, but let me just confirm and extend all these so it's all written out properly. Where's my ends? Hey, not bad. Nailed it. So how I would recommend working through this square root, because you're going to want to simplify this square root. I like to find the first one and then store it in my calculator, and then find the second one and add it to the first one, just kind of working your way out incrementally. And then you can multiply by 0.626, and then you can multiply by 0.374. Just being really careful with your math. I get, once I do this, 30,009. It's going to be super small, or you can be careful and use your brackets. 1 over 25,747. Times 0.626 times 0.374. I haven't done 0.329 minus 0.427, but I have done this 0.1234, whoops, 16895. 04638. Now it does give me in scientific notation, so let me just check. 1, 2, 3, 4. Okay. Once I take the square root, it'll make a small number slightly bigger, which is kind of weird, but only slightly. I'm going to store that. Let's see here, 0.329 minus 0.427. I get negative 0.098. Let's remember what that negative 0.098 is. That's what we're comparing to 0. Is that significantly different from 0, right? Maybe. Depends on the spread, right? Which is that whole thing in the square root. So divided by, recall a, divided by, I have 0.004110358,425. Once I do negative 0.098 divided by that, did I think I did it? Negative 23.84220301. Did anyone else get that? Or did I do something wrong? Yeah? Thanks. Because I was fumbling like crazy on my calculator, so. But the probability of us doing the same fumbles is pretty low, so feels good. Holy cannoli! This tells me that this difference is very different from 0, right? It gets super boggy with the terminology, right? Because now we're talking about the difference in the proportions, and if it's different from 0, right? So what does this look like? you can have something like this on a Z distribution. Z is centered on 0, but these things go to negative infinity and positive infinity, so it's not that. That's not the problem. But here at negative 23.84, let's do a 2 just for good measure. The probability of that happening is very, very, very small. The area in the tail is almost 0, right? So even without the table, I can tell you right now that the p-value, whether it's one-sided or two-sided, right? I take a tiny, tiny amount and multiply it by 2. It doesn't matter. It's still going to be approximately 0. Okay. So if our Z was kind of close to 0 here, right, then they're basically close enough. And at some point, some threshold here, we cross and say, okay, they're probably not the same anymore. But how we communicate that is in step 3, where we have to find the p-value. Now, using the table, oh man, everything's just loading. It's driving me nuts. I better just stay in this one note so that it... Can I just say using the table? We find the absolute value of Z equal to negative 23.842. Is larger than the end value, which is 3.291. So once you have a Z, you know how Z works, right? Because now you're back to where we have been working for a long time now, right? With Zs. And then technically on the upper end, I have positive infinity. If you want to, that one's optional. You don't have to write the infinity. I like to have just the same structure always. And so that's why I put the infinity there. But then I need to know if I have a two-sided or a one-sided p-value. We were doing a two-sided test, and that's from way up here. In our alternative hypothesis, we have a not equal to. So I'm just as concerned if this happened on the upper end, which is still very unlikely. So I need a two-sided p-value. So then the two-sided p-value is going to be between two numbers. Now, at infinity, the area in the tail is 0. You'll never get there, but the two-sided p-value is something bigger than 0, but less than the area in the tail at 3.291. Now the two-sided p-value at 3.291, because I don't have the table, and now my iPad's glitching like crazy. I don't know what's up with it. I think it's because I refused to buy more iCloud storage and now it's punishing me. And I just might cave soon because this is nuts. I refuse. No, can't make me. If you have a table, and I've got spare copies of the table if you want it, but if you have a table, then this is what you would find, right? So now our two-sided p-value is somewhere between 0 and 0.001. That's still very small, right? So now our conclusion, step 4 is the conclusion. same three parts, right? We still have to touch on each of those three parts. I have to compare my p-value to my alpha level. We didn't establish an alpha level, but standard default is 0.05, so we'll keep that. And then what does that mean in terms of my null hypothesis? And then what does it mean in terms of the question? So same standard structure. Since our two-sided p-value, I'm just articulating all the things we found. So that's not hard, but it is kind of being very thorough, which is what I want you to do. So since our two-sided p-value is between 0 and 0.001, it is less than our assumed alpha level of 0.05. It is less than our assumed alpha level of 0.05. Oops. Which means we have enough evidence to reject H naught, right? I moved far enough into the tails to say, okay, probably not the same. Which means we have enough evidence to reject H naught. If you're going to reject it, you should say in favor of what? In favor of HA. Therefore, there is a significant difference, or there was, therefore, there was a significant difference in the proportion of NDP votes, oops, from Kamloops, North Thompson, and Kelowna Center. Neat. That's cool. What if we wanted to know how big was the difference, right? What was the difference in proportions reasonably? Well, if we wanted to know how big the difference is, to find out what the difference was, we use a confidence interval. We use a confidence interval, which would go something like this. I would ask you to construct a find 95%, it's the default, a 95% confidence interval for the difference in proportions. Proportions of NDP votes from Kamloops, North Thompson, and Kelowna Center. We already did the hypothesis test. So just thinking about it, if you build a confidence interval for the difference in proportions, do you expect, if you take P1 minus P2, right, and you found a negative, do you expect this confidence interval to include 0 or not include 0? We rejected H naught, and so I'm expecting 0 to be here, and I'm expecting my confidence interval to not include 0, right? Be way below 0, in fact, if I set up my difference the same way, P1 minus P2, Kamloops versus Kelowna. So let's see if that's true or not on your formula sheet. That is so annoying. All right. I'll just say on your formula sheet, you have this. P1 hat minus P2 hat plus minus Z star. At least you saw it. Times the square root, oops, went overboard there, of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. Let's see here. So this is on your formula sheet, but not written as gross. You don't need the pooled proportion here. The pooled proportion is only for the hypothesis test. So now all you really need are the sample proportions and your sample sizes, and you need a Z star. So let's start with the Z star. We know for a 95% confidence interval, Z star is 1.960. From the table, you'll have the table, so that's fine. But it might be nice to know it too. I won't make you memorize them. P1 hat minus P2 hat. Remembering that I'm using P1 is Kamloops North Thompson and P2 is Kelowna Center. Sometimes these subscripts just kind of happen out of necessity so you can keep track of them. And so I tend to only use them here in the difference because then it's easier to talk about Kamloops versus Kelowna. But 1.960, or maybe I'll do the Z star just one more time. Because what would this look like? PKNT hat times Q hat KNT. You don't have to. Plus P hat Kelowna Center, Q hat Kelowna Center over N Kelowna Center. These subscripts are optional. I like to see them here, but it's really only in the null hypothesis that I'm super obsessed. But it might be nice. Sure. Use question-specific subscripts here too. Not necessarily in the root though, because that gets so gross. We have all these values. 0.327, I want to say, but let me, 329 minus 0.427. did a mashup. .329 minus 0.427. I'm going to scoot this over here because I need room for this square root. Plus minus 1.96 times 0.329 times 1 minus 0.329 is 0.671. 30,009. 0.1 minus 0.427. 0.427 times 0.573 divided by 25,747, I want to say. Let me just confirm those ends. Okay. Hopefully I use the right ones up there. Nothing to it but to do it. I'm going to simplify this fraction and simplify this fraction, add them together. Don't forget the square root. But because it gets so messy, I usually don't write out the middle pieces, and that's okay. You're allowed to do that. I'm going to stop before I take the square root just so you can check your work. But using brackets carefully, we should be able to get away with it. 0.329 times 0.671 divided by 30,009. I'm going to store that. Okay, I get the square root of 0.1234168. 1.6859. And then I'm going to take the root of that so you can check it again. 4. This means I have a standard error of the difference in proportions is 0.0041, blah, 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 times 1.96. I get plus minus 0.0080477800036. I'm going to store that so I don't have to do that again. Hopefully someone else got the same thing. We already know what this difference is. Negative 0.098, negative 0.098. It's not changing. You don't really need to write it out. But for completeness, now I have my point estimate for the difference in the proportions, and this is my margin of error now. Very small. Which means that my interval is going to be from negative 0.098 minus 0.00804, blah, 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 up to 0.098 plus 0.0080477. So minus what I stored, I get negative 0.106047778 up to negative 0.098 plus that. I get negative 0.08995221996. Let's round these maybe to struggling finding a good number of decimal places for this one, because I do want to capture that kind of activity. But here I stopped caring after 6. So maybe let's just do 3 decimal places. Negative 0.106 up to negative 0.090 to 3 decimal places. One thing to remember now is this is not going to be just a proportion. This is for the difference in the proportions, but it also matches what we saw or anticipated earlier, is that 0 is going to be here somewhere, and then my confidence interval is all below 0, right? So that matches what we were expecting to see, and that's always a nice feeling. But one thing to remember is, and maybe I'll write it on the next page, negative 0.106 up to negative 0.090. This is an interval for the difference in the proportions. Yeah. This is a confidence interval for PK and T minus PKC. Right, so not just proportions, but the difference in proportions. So if I get a negative here, right, then that means that Kelowna Center, the proportion of Kelowna Center is consistently higher, right, on both ends than Kamloops North Thompson. Okay? In fact, we're 95% confident that the proportion of NDP votes in Kelowna Center is 10.6%, or is between 10.6 and 9% higher than Kamloops, right? So you can translate that difference into kind of a comparison of the two. Or we can keep it nice and breezy and just talk about the difference in proportions. So we have to interpret our interval, which we do the same way that we have been doing. We are 95% confident the interval from negative 0.106 to negative 0.090 captures the true difference in NDP votes the difference between the difference in NDP votes between Kamloops North Thompson and Kelowna Center. Or another way that we could do it, if we want to step it up just a little bit, we are 95% confident. We could talk about Kamloops North Thompson being just consistently less than Kelowna Center, and maybe that's a more logical way to think about it because we have negatives, right? And so maybe let's approach it from that end. But that's the same as saying Kelowna Center has a higher proportion, consistently higher. So what we could say is we're 95% confident the proportion of NDP votes from Kamloops North Thompson is between 10.6% and I guess I'd have to reverse those, and 9%. Because when I drop the negative, then I have to kind of think about how intervals work, and they're always from smallest to largest. So then 9% and 10.6%. Less than Kelowna Center, right? If I say it's less, then I've taken into account the negatives. So we're talking about the difference between the two and not just the two individually anymore. Wow. Time flies when you're having fun. There. Now you can do it for all the ridings, all the parties. Can you imagine all the fun you'll have? Okay. We have talked about all these. But let's consider this example. So kind of in the same way that we introduced one sample proportion. So here's an example of a survey question and the survey options. And so global warming, scientists predict that global warming may have big effects on polar regions within the next 100 years. One of the possible effects is that the northern ice cap may completely melt. Would this bother you a great deal? Some, a little, or not at all if it actually happened? And so for me, I guess it would bother me a great deal, but doesn't matter. So you pick one of these, and then we've got the survey results from this general social survey. And so what we've got is we've got the general social survey, which is going to represent kind of all Americans. But then they also did the same survey with Duke students, which is a subset of all Americans, of course. But we want to know if there's a difference between these, just kind of the sentiments of the Duke students versus the general population. So here we have the survey results, very similar, right, to what we had with our voting results, right? We could have set this up. We could have NDP, Conservative, Green. Can lump them into others. And we could have Kelowna North Thompson, and beside it, we could have Kelowna Center or Kamloops North Thompson. And we could have organized our information the exact same way, right? And we could have talked about these values here. Okay. So we're going to be interested in one of these categories. Can't remember which one, probably a great deal. Who would be bothered a great deal? So we could talk about the parameter that we're interested in, the difference between the proportions of all Duke students and all Americans, who would be bothered a great deal. We can summarize that by the difference in the population proportions. And we can summarize it with the sample proportions, the difference in the sample proportions. So what we want to talk about are these proportions here. Much in the same way that we did for our voting example, which I think was way better than this one. One of the things I don't like that always throws me off is that I forget to fix every year, is that she's got Duke minus the US, whereas usually I would, if the US is here and Duke is here, I would use this as group 1 and group 2. Just a personal hang up, I think. We've already established all these. We've talked about all these things, but you could build a confidence interval, right? For the difference. So construct a 95% confidence interval for the difference between the proportion of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. And so then you've got all the sample information. That's really all you need. You want to make a 95% confidence interval. And so you have a Z star of 1.96. Plug in your numbers. Somewhere between negative 0.108 and positive 0.086. Thinking about that on a number line, I have a difference of 0 inside my interval. Let's pretend that we calculated it. That tells me that there's not a significant difference between these two groups, right? A difference of 0 is in this interval. It's a perfectly reasonable difference of proportions. And so this tells me that the proportions are not significantly different. Kind of an informal hypothesis test, which we introduced last week, right? We said, okay, well, I can use a confidence interval to get an idea of what my hypothesis test would say, right? Much in the same way that we had a hypothesis test, and then we kind of let that guide us into a confidence interval. I know I'm racing the clock here. What about this? I'll leave this because the solutions are in here. I want you to try making the confidence interval and doing the hypothesis test. So here's the hypothesis test that I want you to do. I'll add is the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap, does it differ from the proportion of all Americans who do, or some better version of that? So that's going to be, whoops, your hypothesis test. You can try it and we'll see. We'll run through it just quickly on Thursday. leave you to it. If you have any questions, let me know. Otherwise, I'll see you on Thursday.